case of the stochastic differential equations or not? And the simple answer is that no. So you have to adjust the formula. So if you see the top formula here, so first of all, we have two processes, x and y, and they follow these dynamics. It's not geometric here. Remember that we have dx equal to sigma dv plus mu dt. So it's a general form of a stochastic differential equation. So one special case would be geometric Brownian motion, for example. So x and y have similar dynamics here, the same STE that we have been seeing so far. And now here you will see the product, d of x, y. So in deterministic calculus, it would be x times d of y, the first term, plus y times d of x, the second term. Okay? But here we have an extra term because this is not deterministic analysis anymore. It is stochastic analysis. So the third term is sigma times mu times dt. Any problem? And the third term is just the product of the volatility. In a way, you can think that it's volatility of the first process times volatility of the second process, and dv times dv gives you dt. So this dt in a way is like dv times dt. Dv times dt, which gives you dt. Now this is true if x and y have followed the same Brownian motion. So if you look at the dynamic of x and y, in both of them we have the same Brownian motion. So I didn't change the notation, right? The notation is exactly the same. So in this case you have this extra term. But if the Brownian motion, like in the second case, so you see these two equations here. So we have the same dynamic, but two different Brownian motion. One of them is b, the other one is b tilde. And these two are assumed to be independent. In this case, you have the same familiar product rule, exactly the same as deterministic analysis. So we have the same rule as deterministic analysis if the Brownian motions are independent. Now, we don't go through the proof of these rules, but we just use them, okay? So time to time we might use them. So any question about the product rule? Okay, so the bottom line is that we have an extra term if we have the same Brownian motion in the dynamics, and we have exactly the same product rule if the Brownian motions are independent. That's it. Now the next section is somehow extension of Ito formula to 2 dimension, 9.4.2. And don't worry, it's a simple extension in the sense that we do not add an extra stochastic process, we just add one time dependent variable, okay? So I'll try again to use the same notation. Let's say we have the same process, dxt is zt dt plus yt d of dt, the same dynamic, and f is deterministic. This time UF is f of t and x. So we have an extra dimension here. So you can think of the time. That's why we call these time-dependent Ito formula. Okay? And f belongs to C12. So this means that one-time differentiable in terms of t and two-time differentiable in terms of x. And now we are wondering that what is d of f of t and big x. Okay, so what is the dynamic of this process? The assumptions are clear. Okay, so again, this notation C12 means just one time differentiable with respect to t and two times differentiable with respect to x. And you can see it in the formula anyway. Now the differential of f of t and xt has very similar form to the one-dimensional case. We only have an extra term due to the time t here. Okay? So look, partial derivative of f with respect to t evaluated at t and xt dt plus partial derivative of f with respect to x evaluated at t and xt. So dxt and d of xt plus half of second partial derivative of f with respect to x evaluated at t and xt dxt squared. Okay? So the form is really similar. We only have this extra term here because we have a time variable, an extra time variable here. So this first term is due to this extra variable that we have. But the rest is very similar, right? It has the same format. Now for me it's easier to memorize this formula, all right? But you can simplify this formula by using these dynamic here. And you can get a simpler form based on z and y. So if you do that, so let's say your dxt is zt plus yt d of dt. So just take this xt, substitute it in here, all right? And dxt squared, this is equal to, so we did this yesterday. The square of the first term is gone because dt squared is gone. 2 times of dt times ddt times zt yt would be 0 again, and therefore the only term is the square of yt dv, which would be yt squared d dt squared, which gives you yt squared dt. Okay? And then take this term, substitute it in here, and simplify. Put the dt term together and put the ddt term together, and then you would obtain this formula here that you can see. Okay? So this formula is obtained by simplifying this expansion here. Now, which one you memorize, it's up to you. Either one will be fine, but it's more preferred when things are simplified. So in your exam problems, try to simplify as much as you can, like for a format like this one that you can see. Okay? So we call this time-dependent Ito formula or a two-dimensional Ito formula. But the fact is that the extra dimension is really deterministic. It's not a very big generalization. Okay? X here is random, but this t here is completely deterministic. So it's a very small extension of the one-dimensional case. So we call this time-dependent Ito formula. Time-dependent Ito formula. So one big mistake is that sometimes this small t, this extra dimension, is confused with the index of the Brownian motion or either with the index of x. All right? You have to look at these t independently. Okay? The x here can be a substitute for either the whole xt or the whole dt. But this extra dimension t is not for this index of d or index of x. We can see that in examples. So I don't really simplify this here, but it's a very simple exercise. It's not difficult. Okay? Now the next example. So any question about this extension here? Okay? So the next example is actually what you have in your note here. And I always try to keep the notation exactly the same thing as much as possible. But for this one, I slightly changed the notation. I think it helps understanding the example better. All right? So this is the same thing. I just write it in a simpler way. Suppose that the solution of S d d of xt equal to xt to the power of 3 dt minus xt squared d of dt. So this is your differential equation, and the starting point is 1. So x0 equal to 1 has the following form. So we assume that the solution has a form. What's the form? Xt equal to f of t and bt for some deterministic function f of t and x. Look, this is a deterministic function, so I use small text, all right? Now solve these SDE. Solve these SDE. Now what does this mean when we say solve these SDE? So here we have a function of t and bt, which means that find f, basically. Okay? Solve these SDE, which means find f. Find function f, t, and x. Okay. So let's read it together. Suppose that the solution of SDE dxt equal to xt cubed dt minus xt squared d of bt with starting point of 1, which means x0 equal to 1, has the following form: xt equal to f of t and bt. Now you don't need to be worried about that. So suppose that this assumption is given to you. I made this clear because it's not always clear why xt should have this form, why xt should be a function of t and bt, but I give this to you. You can make this assumption. Right? So now that we know x is a deterministic function of t and Brownian motion, then the solution means that just simply find f. If we have this deterministic function f, then we have our solution. All right? So the rest of the problem is to look for this deterministic function f. So any problem about the example? Do you understand that? All right, you can start by calculating the differential of xt based on the formula that you have here. So look, d of xt equal to, we know that xt has this form, so d of f of t and bt. So this is by the assumption. If I didn't have this assumption, I couldn't write this equality. But now that I have the assumption, I can write the equality. Now, the next step is just use the Ito formula that you have here. Okay? So this will be partial derivative of f with respect to t dt plus partial derivative of f with respect to x d of dt plus half of second partial derivative of f with respect to x2 d of bt squared. So I didn't really do anything strange. I just directly use the Ito formula that I have here. Look, instead of x, I have b, so partial derivative of f with respect to t. I didn't write the rest, just to simplify the notation. So partial derivative of f with respect to t stands for the whole thing here. And then partial derivative of f with respect to x, d of dt plus half of second partial derivative of f with respect to x, and d of pt squared. So sometimes to simplify the notation, we just write partial derivative of f with respect to t instead of evaluation and t and x. Okay? So this is to simplify the notation. You can write the complete term if you want. Now this will be partial derivative of f with respect to t dt plus partial derivative of f with respect to x d of dt plus. So here the only term that we need to simplify is dv squared, which we know is dt. So our second partial derivative of f with respect to x2, and this will be dt. So here, in order to emphasize partial derivative of f with respect to t actually means partial derivative of f with respect to t evaluated at t and dt, and the same thing for x. Now sometimes people also use partial derivative of f with respect to dx, but I think this is much more obvious. Okay, the next step is to simplify, put all the dt term together and put all the ddt term together. Okay. So here d of xt is equal to partial derivative of f with respect to t plus, so I have one dt term here, and half of partial derivative of f with respect to x2 dt plus partial derivative of f with respect to x d of dt. So I obtained this by Ito formula, but by assumption, dxt also has this form. So dxt is equal to xt cubed dt plus minus xt squared d of dt. The second equation is by assumption that we have. So on the left-hand side, I have dxt. So the right-hand side must match as well, right? So these two equations must match as well. So if this is true, then from these two equations, I will get that partial derivative of f with respect to t plus alpha partial derivative, second partial derivative of f with respect to x squared. This must be equal to x f cubed, right? So this must be equal to f cubed. This is one equation. The second equation is partial derivative of f with respect to x is equal to minus f squared. And if you're wondering why I replaced x by f here, why I didn't write x cubed, you can write x cubed, but by assumption x is just f, right? So here, this is actually f t and bt cubed, and this one is f of t and bt squared. We just write as f cubed and f squared. Okay? So any questions so far? So again, you can see that why this assumption is useful, because if I don't have the form of xt as f of t and bt, I cannot replace x cubed by f cubed. I cannot replace x squared by f squared. Okay? Now the rest is a deterministic problem now. So you have a system of equations and you have to solve. So here we have two equations and we have partial derivatives. In general, it's not easy to solve a system of partial derivatives equations, but in this case, it's simple enough that without any specific knowledge, you can solve it. Okay? Now, how to solve them? I will put it over here. So the rest is really deterministic analysis to find f. Okay? So I write down the equation again, partial derivative of f with respect to t plus half of second partial derivative of f with respect to x squared. This must be f cubed. And partial derivative of f with respect to x must be minus f squared. Same thing that we have. Now to solve this, from the second one, take another derivative. So take derivative of partial derivative of f with respect to x. So this would be second partial derivative of f with respect to x, which would be minus partial derivative of f2 with respect to x. So this gives you minus 2f times partial derivative of f with respect to x. So this is by derivative rules. Now take these partial derivative, second partial derivative of f with respect to x substituted in the first formula. So from here we get partial derivative of f with respect to t plus half of. So here I have minus 2 times f, partial derivative of, and actually we can even simplify this more here. So I have minus 2f times partial derivative of f with respect to x is minus f squared. So I can substitute it for minus f squared. So this gives me 2f to the power of. So if I substitute that, it would be plus half times 2f cubed equal to f cubed. So you can see that f cubed and f cubed cancel each other. So it would be partial derivative of f with respect to t equal to 0. And what does this mean? When the partial derivative with respect to t is 0, it means that f does not depend on t. Okay? So from here means that f is just f of x. So there is no extra time t here. This was not obvious from the beginning, but this partial derivative of f with respect to t equal to 0 determine this. So no time dependent. So when we don't have time, it means that we have just one dimension, and instead of partial derivative, we only have the strong one-dimensional derivative. So since we don't have any time, then partial derivative of f with respect to x equal to minus f2. This is just f prime equal to minus f2. Okay, so this is just, if I write it, df divided by dx. So I don't use partial anymore because I know that there is no time. Therefore, this partial derivative with x is just a strong derivative with respect to x. Now, how do you solve this? You can use a separation of variables. So this is minus or df divided by f2 minus df divided by f2 equal to dx. So I put all f variables in one side, all x variables in one side. This is called separation of variables. This is a very standard technique in ordinary differential equation. Now take integral of both sides. Okay, so from here the left hand side is minus 1 over f, and the right hand side is just x plus a constant, let's call it c. Minus here, I don't think so, right? Just plus 1 over x, right? Wait, don't change it. have plus 1 over f equal to x plus c. So that's fine. And next is f is equal to 1 over x plus c. So this is the form of our function. Okay, this is f of t and x. If I want to be more precise, you can write there for either f of t and x, both are fine. So this is the deterministic solution of this system of equation. But I want the solution of my problem. Remember, the solution was xt equal to f of t and bt. So substitute this x by bt, it gives you the solution bt plus c. Okay. Now I need to obtain c. So how do you obtain the c? We know that x0 is equal to 1. That was given by the problem. So let's calculate this for x0. So it would be 1 equal to 1 over b0 plus c. So b0 is 0. So this gives c equal to 1. Right? So by the definition of Brownian motion, we know that b0 is 0. So b0 is 0, and this gives you c equal to 1. Therefore, xt is equal to 1 over bt plus 1. And that is the solution that we look at. I think it's this here. 1 over bt plus 1. Okay, any problem here? So here you can see that how powerful the Ito formula can be. That you can start from one stochastic differential equation, and then it will lead you to get the solution. Okay, the next section, 9.4.3, is again another example, but a very important example that we need to discuss it here. So these OU processes, or Ornstein-Uhlenbeck processes, are very important processes in finance. Like you can see them as the asset evolution processes. When we study interest rate, in the second part of this course, we will also visit this kind of processes. Okay? So these are very important processes, and we need to know their dynamic and their solutions. So I simply write solve dxt equal to minus gamma xt dt plus sigma d of dt, and we call them OU processes. So OU process, and here gamma and sigma are constant. In general, they don't need to be, but here we assume that they are constant. And yeah, this is all we need, and then we have to solve these equations, this SD equation. So in the previous example, we saw a technique for solving SDs, right? We assumed a form for the solution, and then we solved the problem. Now here you can see another technique to solve the stochastic differential equation, and how this works. So solution. So in this kind of approach, you suppose that there is no sigma term, okay? Suppose that there is no volatility. So if you ignore the Brownian motion, this is a very simple differential equation, and the solution will be c e to the power of minus gamma times t. Be careful, this is not gamma index t, it's just gamma times t. So this is the solution if there is no Brownian motion. If no Brownian motion. Okay, this will be the solution. But once you add the Brownian motion, then you should not expect that you will have the same solution. But you can hope that the solution will not be deviated that much. Alright? So instead of C, I hope that I have, let's say, U, a process U index t, and then e to the power of minus gamma t. And we hope that the solution will be of this form. Now this is just a guess. Okay? It might work, it might not. So if this is not a good guess, then you have to come back, change it, and find a different form. All right? So all this second approach is based on the fact that you find or you have a good guess of finding this form. So if you solve this for u, ut would be e to the power of gamma t xt. All right? Now apply Ito formula on du, or calculate the differential of u. So this is of this form. Look, f of t and x, where f of t and x is x times e to the power of gamma t. So if you substitute this x, f of t and big xt here, so if you define this deterministic function f by x times e to the power of gamma t, then ut is just f of t and xt. So ut is just f of t and big xt. So if you substitute this small x by big xt, then you exactly have ut. Now apply the Ito formula. So from here, du would be, so partial derivative with respect to, I write it again, with respect to t dt plus partial derivative with respect to x d of xt plus half of second partial derivative with respect to x d of xt squared. Okay. So now calculate that. D of ut equal to, so partial derivative of f with respect to t is just gamma x e to the power of gamma t. So it would be gamma b xt e to the power of gamma t dt plus partial derivative with respect to x is just e to the power of gamma t. So it would be partial derivative with respect to x, d of xt, plus, and second partial derivative with respect to x squared is just 0, because there is no x anymore. Partial derivative of e to the power of gamma t with respect to x is 0. So the third term is 0, and now you simplify and see what you get. So d of ut, you have to write it. So if you substitute this dynamic of x, dx here, or this, if you do this substitution and simplify, then you will obtain d of ut equal to gamma xt e to the power of gamma t dt minus gamma xt e to the power of gamma t dt plus sigma e to the power of gamma t d of dt. Now the first and the second term cancel out each other, so it will be d of ut equal to sigma e to the power of gamma t d of dt. Now take integral of both sides, so this will give you ut equal to sigma integral 0 to t e to the power of gamma s d of ds. But what was ut ut was xt, and we have a constant, right? Well, c a constant. Okay, but ut was x to the power of x times e to the power of gamma t. So from here, multiply both sides by e to the power of minus gamma t. So this gives you xt equal to c e to the power of minus gamma t plus sigma e to the power of minus gamma t integral 0 to t to the power of gamma s e of s. So now we found s, we only need to determine c. So let t be 0. So we have x0 equal to e to the power of 0 is 1. So we have only c here plus, if you let t be 0, integral from 0 to 0 is 0, right? So it will be plus 0, and therefore c is just x0. And so xt is x0 e to the power of minus gamma t plus sigma e to the power of minus gamma t integral 0 to t to the power of gamma s e of t. Okay. Now I think in the solution they take gamma t inside and update. So this final solution here is exactly same as this solution here, but they just take e to the power of minus gamma t inside the integral, because the integral is versus s, and you can do that, okay? But you can also leave it just like that. That's perfectly fine. Okay, is there any question about this solution? All right, so we can move to the next section, 9.5. So in this section, there is a very important identity that we call it ethos isometry. And why this isometry is so important. Let's start by this example that what is the distribution of 0 to t, g of s, d of ds, okay? So what is the distribution of this process? What is the distribution of these process? Okay. Now, if you look at this slide here, you see that integral of 0 to t gs d of ds is based on this sum here. This is what we did. We did something similar for integral of 0 to t ds d of ds. So we have this identity here. Now if you look at the sum here, it's the sum from I from 0 to n, and then you have g. So g here is deterministic function. The function. Okay. So look at this sum here is the sum of the difference or the increment of Brownian motion. So the increment of Brownian motion is this bracket here, and by the property of Brownian motion we know that is a normal distribution. And we know that the increments are also independent. So this sum here is the sum of independent, identical, normal distribution. And from statistics, we know that the sum of independent and identical normal distribution is again normal. Therefore, the whole sum inside the bigger bracket is normal. All right? the whole sum is normal because it's the sum of normal distribution. Now this G here, because it's deterministic, it doesn't affect the distribution. Okay? A deterministic constant or coefficient doesn't affect the distribution. So this is normal because the sum of normal is again normal, and very simple word. Now what's not obvious is the limit. So if you take the limit, is this still normal or not? Yes, it's normal, we don't prove it, we accept it. So we get this identity that integral 0 to t g of s d of ds is normal, but we need to find the mean and we need to find the variance. So if we find the mean and if we find the variance, then we are done. And this is where that you use the Ito isometry for the variance. Is there any question or not? So far we know that integral 0 to t gs d of ds is for sure normal for a deterministic g. So if we find the mean and if we find the variance, then this distribution is completely determined. All right, and that's what we're doing here. So the mean of integral 0 to t g of s d of ds, by a very similar way that we did it for integral 0 to t ds dbs, you can show that this is 0 by a similar approach to the one that we calculate integral 0 to t ds d of ds, and we show that this is 0. Do you remember? We show that this expectation is 0. Now use a very similar approach and you can show that this is also 0. So if you remember, you take the expectation inside the sum and you use the property of Brownian motion, and then you can easily show that this is 0. So the mean, now we know the mean is 0, and we need to obtain the value. Now this is a very important part of Ito calculus, so please pay attention. Look, I need to calculate variance of 0 to t gs d of ds. So by definition, this is expected value 0 to t gs d of ds to the power of 2 minus the expected value 0 to t gs of ds, the whole thing to the power of 2. But we know that the mean is 0, so this would be just equal to expected value of 0 to t gs d of ds to the power of, okay? Now, we only need to calculate this expected value and then we're done. And this is by Ito isometry. So by Ito isometry, this is equal to integral 0 to t gs squared d of s. Okay? So look what's happened. In a way, in a very simple way, you square the integrand, which is g squared, and you change b to s. So I have ds. I don't need any expectation now. Why? Because g is deterministic, and this is a deterministic integral. So this would be integral 0 to t g to s d of s. Now that I have the variance and I have the mean, therefore the distribution is completely determined. So I know that integral 0 to t gs dds is normal with mean of 0 and variance of 0 to t g to s ds. So just one thing about the Ito isometry what we use here is a special version of a general Ito isometry. So Ito isometry, and it's this one. Expected value 0 to t. I think the notation is used as z. Z is squared e of ds. So the same thing happened there. You take integral 0 to t, and sorry, we don't need square here. Now on the right hand side, you square the integral. You change b to s, so ds. But in general, z need not to be deterministic. Therefore, we need to apply an expectation. So z here either deterministic or random. So if it's deterministic like our G, you don't need expectation. But if it's random, then you have to use the expectation. I think it's the same notation. I tried to keep the same notation here. G. So in your note, it's Z bracket open S. It's the same as ZS. And in fact, it's better to write the stochastic processes as Z index S. But in your note, it's like Z bracket open S. So here, ZS is just same as Z bracket open S, as you know. Okay? The Ito isometry is very powerful in the sense that it's an identity that in which the Brownian motion disappears. So look at the left-hand side. Instead of B, I have S. But instead of, I forgot. So I take the square here inside the integral, and I change b to s, okay? So look at the changes. This b is changed to s. These two here is taken inside. Now if instead of z I have g, then I don't need the expectation, because g is deterministic, and then there is no randomness. So in fact here we could have an expectation, but the expected value of this is just 0 to t, g to s, ds. And you use this identity a lot. So try to understand it. Okay, so we're done. Unless you have any questions, then you can come and ask me, okay?